Question 9. This question is about gravitational potential. A. Define gravitational potential at a point in a gravitational field. C. This is Earth, and there is an object at P point, R distance away from the core, and the mass of this is 1 kg considered. Now, this is infinity. Okay. So, imagine you are bringing this 1 kg mass from infinity to this point. So, in order to do that, you need work done. So, the work done required to bring this 1 kg object from infinity to a point P, which is r distance away from the core of the planet, is called gravitational potential at this particular point, which is denoted by V, which is minus k minus gm by r, where g is gravitational constant, m is the mass of this, and r is the distance from the core. Okay, and it is joules per kg. The unit is joules per kg. So you can write potential, gravitational potential at particular point is work done per unit mass at a certain point in point r distance away. So this is how you answer this. You can answer this in words, or you may draw the diagram and write down the answer in words. B, a planet has a mass of m and radius r0. The magnitude of g0 of the gravitational field strength at the surface is this, where g is the gravitational constant, big G is the gravitational constant. Use the expression to deduce that gravitational potential V0 at the surface of planet is this. Now you see, V0, we have seen gravitational potential is work done per unit time, work done per unit kg at certain point P, which is r distance away from the planet. We've seen that, and this is equal to minus gm by r. This is the mass, this is point P where there is 1 kg. You can consider this is radius, and here it is V0. This is R0, we can consider. Now you see, there will be a gravitational field strength or gravitational acceleration acting towards the Earth. Okay. Now, how to find out the relation between V0 and G0? You see, they have mentioned a relation between G0 and Gm. So from here, we can write G0 R square is equal to Gm. And I can replace this Gm with G0 R square. So minus G0 R square by R. Okay. So this and this square will get cancelled. So finally we are left with V0 minus G0 R. So this is how we are able to show that V0 is equal to minus G0 R. Okay. Not G0 R0. Sorry. Now see, the graph below shows the variation with the distance r from the center of the planet of the gravitational potential V. The radius r0 of the planet is 5 into 10 to the power 6 meters. Values of V are not shown. So r lesser than r0, as you can see here. Use the graph to determine the magnitude of the gravitational field strength at the surface of the planet. So you see, the radius of the planet is 5 into 10 to the power 6. which can also be written as R0 is equal to 5 into 10 to the power 6 meters, or I can write 0.5 into 10 to the power 7 meters. Now let us go to the graph. So 0.5 into 10 to the power 7 meter is here. So this is the surface. See, radius of the planet means at the end at 0.5 into 10 to the power 7 meters or 5 into 10 to the power 6 meters R0. It is nothing but the surface you are going to find. Okay. Now this is the surface. As you can see, V0 here is around 3 minus 3.5, 6, 7, 8. 3.8. Now question, let us go through the question first. Use the graph to determine the magnitude of gravitational field strength at the surface of the planet. Just now we have found out V0 is equal to minus G0R. Now let us take the magnitude of it, because if I consider minus, then there is going to be a problem. The gravitational field strength will have a sign that is minus. We don't want that. I don't want you to get confused. Let us stick to the magnitude. Yes. Since they are asking us to find out the magnitude. Now, you see G0 is equal to V0 by R. R here will be R0. So, we know R0. What is the V0? V0 at R0 at the surface is around 3.8 into 10 to the power 7 joules per kg. So R0 is 0.5 into 10 to the power 7 and V0 at the surface is around 3.8 into 10 to the power 7. So 10 to the power 7, 10 to the power 7 will get cancelled. Now solve this. 3.8 by 0.5 is going to give me 7.66. It will be Newton per kg, since they're asking for gravitational field strength. G0 is this. So let me make a note of these things. V0 is 3.8 into 10 to the power 7 joules per kg. G0 is 7.6 into 10 to the power, sorry, not 10 to the power, just Newton per kg. Okay. Now they're asking a satellite of mass 3.2 and 10 to the power 3 kg into 10 to the power 3 kg is launched from the surface of the planet. Let us draw it. Draw it where? Let us draw it here. From the surface of the planet, it is launched. It will be launched either like this or like this. Now, tangentially, it will be launched. Okay, like this. Let us consider. Use the graph to estimate the minimum launch speed that satellite must have in order to reach a height of 10 to the power 3. So from here to here, okay, it will be definitely orbiting. So it wants to reach a orbit which is having height from the surface is 2 into 10 to the power 7. So it should be bigger, much bigger. It will be somewhat like this. Okay, to reach this, from here to here is 2 into 10 to the power 7. And this radius, we know R0 is equal to 0.5 into 10 to the power 7. Okay. Now, from center to this, the distance is, let us consider R, which is 0.5 plus 2 into 10 to the power 7, which will give me 2.5. 10 to the power 7. So, what is the minimum velocity required in order to reach this orbit? So, remember, R is 2.5 into 10 to the power 7. Now, let us ignore the fact that there is air resistance. Okay. So, in this case, we can imagine this system to be conservative system. Okay. In a conservative system, total energy change is del Ke plus del Pe. Okay. So I can write which is equal to 0. So I can write del Ke is equal to minus del Pe. Okay. Since potential energy is actually negative, if you look at the formula of gravitational potential and it's negative, I can eventually write this is plus del P. Okay. We'll use this concept or this relation in order to find out the velocity required. Now at 2.5, the potential is gravitational potential V final, let us consider, which is 0.8 into 10 to the power 7. As you can see, 0.5678 joules per kg. And at the surface, it is here, right? V0 is 3.8. 3.8 into 10 to the power 7 joules per kg. Now, you see, I can write half m Ke is equal to del Ke is equal to del P, right? Potential energy. Del K, since it will start from the rest itself. So, let us consider this to be half mv square. This is the velocity we want to find out. Potential energy. Now, gravitational potential energy, U is gravitational potential energy, which is m into V. Okay. V is the gravitational potential. So, I can write mv. This is minus, right? Minus, and there is another minus. mv final minus mv0 initial. So if I take m common, this m and this m gets cancelled, so I'm left out with velocity is equal to root 2 vf minus v0 divided by vf minus v0 divided by nothing in the denominator. That's it. So root 2 into v0 is 10 to the power 3. Minus 0.8 minus of minus 3.8. I'll put this 10 to the power 7 outside because this is this is same for both. 2 into, now solve this thing. So minus minus becomes plus. So root 2 into minus 0.8 plus 3.8 into 10 to the power 7. We are going to get 7.745 into 10 to the power 3 meters per second. So this is the velocity at which it must escape so that it reaches a height of 2.2 into 10 to the power 7 meters above the surface of the planet, and it rotates in the orbit.